Okay, so last time you saw that when you apply forces on an extended object, so here's a ladder and let's say somebody's climbing up the ladder. So here are the forces acting on the ladder. Okay, the weight of the person, the weight of the ladder, the wall pushing back on the ladder. Okay. So when this force is perpendicular to the wall, what are we assuming? When, I'm sorry? So when this force is perpendicular, that means there's no friction on the wall, okay? And there's this static friction force. Why is this a static friction force?
It's static, it's not moving.
Yeah, it's not moving, and you hope it doesn't move, right? So this is a static friction force. There's the normal force. And so this person that's climbing up the ladder, this person sure as heck hopes that the ladder doesn't move. And for the ladder not to move, there are two conditions that need to be satisfied. Okay. The sum of all the forces acting on the ladder should add up to 0. Okay. And in all the problems we consider, these forces will be only two-dimensional, so this is really two equations. Okay. And the torques of all these forces should add up to 0. Okay. Now this is a sort of subtle point. When is only this condition enough to ensure that an object is at rest? Yeah. So when do you not need to worry about this equation? If all the forces acting were going through the center of mass of the object, then you don't have to worry about all of that. Okay? So, but for extended objects, so you have to make sure that these two conditions are satisfied for the object to be in static equilibrium. Okay? So we learned that. And your statics course will be based entirely on these two equations. Okay? All right, then we were starting the subject of elasticity. Okay, so many of our structures, when stressed meaning, so for instance on a bridge, when a car drives by on a bridge, you're adding additional stresses and the structures will deform. Okay, so when a truck drives by, each of these cables will lengthen. Okay. And what you want is, once the car drives away, you want the cables to go back to their original shape. And you want the cables to do that millions of times. And you want the cables to exhibit elastic behavior. Okay? Ideally, an infinite number of times. Okay? And so what we're going to do is we're going to study 3 different kinds of stresses that will apply to our structures. Okay? So we'll apply tensile stresses, okay, when the predominant dimension is the length, and the most noticeable deformation will be in the length of the object. This is a tensile stress. If you apply a force that's compressing the object, that's called compressive stress. Okay? We will apply volume stresses, bulk stresses. Okay, so if you throw an object underwater, the pressure on it is perpendicular to the objects, all the faces of the object, and the volume of the object will decrease. Okay? So you're applying bulk stresses to them. Okay? We want to study that behavior. And we also apply shearing stresses. Okay? So now shearing stresses are applied to solid objects. A liquid cannot bear shearing stresses. Okay? So those are the 3 kinds of stresses we'll apply, and we'll study the deformation. Okay? And what we are interested in is in the regime where when you remove the stress, what do you want happening? Go back to its original shape. Okay? And that's so we want to study elastic behavior. Okay? All right. All right, so you're here in this object, you're applying a tensile stress. Here you're applying a compressive stress. Okay? So when you apply tensile stress, the length of the object increases. When you apply compressive stress, the length of the object decreases. Now here's a very interesting point. I'll jump the gun and show you this table. Okay, so this is the tensile strength. The strength tells you what kind of stress do you need to apply when the object is compromised, meaning it breaks. Okay, so tensile strength is what tensile stress you apply when the object breaks. This is compressive stress strength. Okay, so look at this number for concrete. It's 2 megapascals, and we'll understand the numbers in a little bit for tensile stress. But the compressive strength is 20 megapascals. Okay, what that number is saying is this is 10 times bigger than that. What that number is saying is a concrete pillar is 10 times stronger under compressive stresses than tensile stresses. Okay, so what that means is let's say, I'm just making up numbers, you hold a concrete pillar, and if you pull with a force of 1,000 pounds and it cracks, how many pounds do you have to apply to the same concrete pillar before it cracks?
10,000?
20 times. Oh, 10,000. Yeah, 10,000 pounds. Okay? So it's 10 times stronger under compressive stresses. Okay? So you keep this in mind. Whenever in structures, when you build structures, so for instance, this is a structure where the largest force is a compressive force. And the smaller forces are tensile forces, and we'll come to that. Okay, so this is the kind of stuff you want to learn, and then wherever it's strongest, that's the largest forces are applied accordingly. Okay, so we'll come to that. All right, so now let's look at this again. Here is a rod. You're applying a tensile stress. You're stretching it. Okay, so let's say you apply a 100-pound force and the rod stretched. Okay, we saw that it'll stretch a certain amount and then stop. And why is that? Why did it do that? Do you guys remember? So let's say you have a rod and you applied a 1,000-pound force and it stretched 10 millimeters and then it stopped. Why did it stretch 10 millimeters and then stop? Okay, so here's what we talked about. Okay, so this solid is modeled like this. Okay, so here are the atoms arranged, and the forces between atoms are modeled by these springs. When you apply, let's say, 1,000-pound force like this on the rod, what happens is each of these little springs stretches. So when this spring stretches, this atom is being pulled back by that guy. Okay, this atom is being pulled back by that guy, and so on. Okay, so here is a side view. Here is the 1,000-pound you apply. This atom got pulled by that much. All these atoms get pulled an equal amount. Okay, and so this guy is pulling him back. This guy is being pulled back, and so on. And the amount of stretch corresponds to all these forces adding up to that force. Okay. What would happen if this was increased from 1,000 pounds to 2,000 pounds? All those forces would double, and they would add up to that. Okay. So the rod stretches such that the restoring force is equal to the deforming force. Okay, or the reaction force is equal to the deforming force. Okay. All right. So here is a tensile strength. Tensile strength for concrete is 2 and compressive strength is 20. Okay, so this is the kind, and for cast iron, so this uses cast iron. For cast iron, the compressive strength is 550 megapascals, and it's 100 tensile stress is that. So a cast iron is 3 times stronger under compressive strength than tensile strength. Okay, so what you want to make sure is the biggest forces are compressive forces. Okay, so let's see how that is incorporated in a structure. Okay, so what is it that you want to keep in mind? the largest forces in your structure should be compressive. The little forces can be tensile. Okay, so let's look at this bridge. Okay, I'm going to draw a simpler diagram here. Okay. Okay, so let's say the bridge, what you want to support is the bridge with its vehicles and all. Let's say you want to support 1,000,000 pounds. Yep. All right, so you put together a bunch of cables. If you put together 100 cables, each cable is supporting 10,000 pounds. Okay, so each cable is under a tension of 10,000 pounds, meaning the cable is pulling this down like that, and it's pulling this holding this bridge up with 10,000 pounds. So all these cables are only doing 10,000 pounds worth of job. Okay. Now let's see what do these guys do. All right, so each of these cables is pulling down with 10,000 pounds. And what they end up doing is all these forces get translated into forces like that on this big cable. And that big cable, these forces pull down on these pillars, okay? And these pillars, they feel a force like that. Yep. And how large is this force? So how large is this force? That's half of this, 500,000 pounds. And that's what's supporting this 1,000,000 pounds. So this 1,000,000 pounds got turned into 2 500,000-pound compressive forces. Okay? And these tensile forces that were stretching the cables were only 10,000 pounds. So the small forces are tensile and the largest forces are compressive. Okay? So that's the idea of the design. Okay? And why do we build suspension bridges?
You don't have to make 1,000,000 of the bottom parts and cover up all the.
You can build a bridge high and it takes very little material. Okay, so you can build a Roman bridge, but you can't build it as high and it takes a lot more material. Okay, so what is the idea of the construction industry? Bigger, stronger, lighter, cheaper. Okay, and those are good things. Okay. All right, so and look at the bone, it's also stronger under compressive strength. Okay. Marble is polycrystalline, so it's the tensile strength varies for the marble, so you can't give a standard value. Okay. All right, so you saw that if this rod is made of cast iron, it's stronger under compressive forces, stresses than tensile forces. So if this rod were to crack, it would crack somewhere there. Okay, it never cracks there, unless of course it's defective at the bottom. Okay. All right, so if we want to become familiar with two terms, stresses and strains. Stress is equal to the external force acting on the object per unit area. Okay, how large is the force? But what's relevant to us is the force per unit area. Okay, so stress is force per unit area. Strain is a measure of the deformation. Okay, so strain measures this deformations. What's relevant is, okay, so it's what is the percentage deformation is what's relevant. So this rod, in its length increased by delta L. So strain is given by delta L by L. This is strain. Okay? So the percentage deformation is what is relevant to us. Okay? So strain is a measure of the degree of deformation. Okay? And then we define elastic moduli for various materials. Okay? Elastic modulus is stress, which is the force per unit area, divided by the deformation, divided by the strain. Now here's the deal. Okay, if for a given stress, for a given force, if the deformation is smaller, the elastic modulus is higher. Higher the elastic modulus, stiffer the material. Okay? And generally stronger the material. So, higher the elastic modulus, stiffer the material. It's harder to deform it. Okay. All right, so there are three types of modulus. We'll consider Young's modulus, when the solid changes, the predominant change is the change in length. Shear modulus, so this is, you are applying shearing forces, and this is the deformation. Okay, smaller this deformation, higher the shear modulus. Okay, so for instance, you can take a textbook and apply shearing forces, and the textbook will deform more compared to, let's say, a solid piece of metal. Okay, or a piece of wood even. Okay, a piece of wood would deform more than a block of steel. Okay. Bulk modulus measures the volume deformation. Okay. So bulk modulus measures the resistance of solid or liquid to a change in volume. And you know, this is, so you would be interested in this kind of stuff. So here's an example I can think of. So let's say you're designing a sub with windows. We talked about this last time. And the bulk modulus of the steel hull and the windows are different. And you want to go deep in the sub and have the windows not leak. Okay, so you have to keep all that kind of stuff in mind. All right, so Young's modulus is what we use when the deformation is in the length of the object. So the tensile stress is force per unit area. There's the force, and the relevant area is the area of cross-section. And the strain is change in length divided by the original length. Okay, so this is the percentage change in the length of the object. Okay, and so that's Young's modulus. Okay, this is dimensionless, meter divided by meter. That cancels. So strain is dimensionless, and stress is force per unit area, Newton per meter squared. Okay. And again, when we are talking about pressure, this unit is called pascals, but here we won't call it pascals. We'll just leave it as Newton per meter squared. Okay. Okay. What this graph shows you is the following. So for many wires, they will have this kind of graphs. Okay. And we'll see in a second why we have this kind of graphs. All right, so what this is telling you is this is the stress applied, and this is the strain that the wire undergoes. Okay, so what this shows you is this is the proportional limit or the elastic limit. If you apply this much stress, this is the strain it undergoes, and when you remove the stress, it'll go back to its original shape, the wire. You apply this much stress, it'll stretch that much. You remove the stress, it'll go back to its original shape. Okay, you apply this much, this is the proportional limit. So, and beyond that point, now you're changing the structure, and it's not going back to its original shape. This yield point defines now permanent deformation. Okay. All right, going back to our structure, our bridge. Okay, a car went by, this wire stretched, you want it going back. Okay. And you want to keep, this cable to keep doing that forever and ever, ideally, but that never happens, okay? So when you're designing this bridge, what do? You assume the biggest load you'll support. What will be the biggest load you'll support? Well, fill the bridge with all the semis, fully loaded semis. That's presumably the largest load you know. And for that load, you want to make sure that the stresses on each wire is somewhere there. You don't want to be anywhere near there. Okay? If you're anywhere near there, then the wires will deform permanently, and you don't want that. Okay? So depending on how much money you've got to build the bridge, the lower you are, the better. The lower you are, the more the bridge costs you. Okay? Or the thicker the wires have to be. Okay? But anyway, so that's what you want to do. All right. Shear modulus, you're applying shearing forces. These are equal and opposite forces on opposite faces. Okay. Now it turns out that the further apart these four faces are, the more they will deform. Okay, and you can see that. If you were this close, they would only deform that much for the same material. Okay. Okay, the shearing stress is force per unit area. And the shear strain is, okay, how much did the top face move relative to the bottom face? The bottom face is fixed. Okay, and again, these two forces have to be equal and opposite. Otherwise, if they were not equal and opposite, if this force was larger, this guy would move to the right. Okay, and you don't want that. Okay, so these are equal and opposite. This shear strain is this displacement, delta x, divided by how far apart the planes are. Okay. So that's the shear strain. Bulk modulus, okay. You are changing the volume of the object, and the only way you can do that is if you apply a force perpendicular to the faces. So here you're decreasing the volume, and that's generally what happens. The volume of a solid wouldn't change even if you if you put it in perfect vacuum. Okay. So we are mostly interested in compressive deformations. Okay. That's the kind of stress you normally apply. Okay, so the bulk modulus is volume stress, force per unit area, divided by change in volume divided by volume. Okay, so percentage change in volume. All right, and then they're throwing this negative sign. Why do they have the negative sign there? So most of the time, the change in volume is negative. So negative of negative, the bulk modulus will be positive. Okay. Again, the smaller the deformation, greater the bulk modulus. Okay. So again, all these elastic constants are important, and here, so you always have a table like this. So you see this, aluminum has a Young's modulus of 7 times 10 to the 10 pascals. Iron has 21. Okay, so what that means is iron is 3 times stiffer than aluminum. So if you take an aluminum wire and so again, Young's modulus is force. Okay. So you take an aluminum wire and a steel wire, same dimensions, and you apply similar forces. Since the Young's modulus for steel is 3 times greater, the deformation in steel is 3 times less. That's what those numbers mean. Did you guys understand that? Okay. Look at this. This is interesting. Human hair. Aluminum is only about 7 times stronger than that. Human hair. Yeah. silk is 6 times stronger than human hair. A spider thread is supposedly very strong, but it's weaker than silk. Okay. All right, now that you are experts at this kind of stuff, so here's what we'll do. We'll apply your knowledge. Okay. Again, concrete is stronger under tensile or compressive stresses? Compressive stresses, okay. So here's so under tensile stresses, it's weaker. So let's say if you build a bridge like this, a car goes by, what happens? Okay, so there is the bridge, and every time a car goes by, it'll buckle like that. Okay, so this bottom part stretched, the top part of the road compressed, so cracks will develop here over time. Okay, so we want to fix that. Okay, so here's what we do. So what you do is you take these steel rods. When you build these spans, you take the steel rods and stretch them, put them under tension, then pour the concrete. So you have these steel rods that are under tension, and then you pour the concrete slab on top of it. And once the concrete dries, you let go of the tension on the cables, on the rods. So now, in steady state, the concrete is under compression. And then you lay the spans, and then when a road goes by, a car goes by, it was compressed to begin with, it only goes back to its original shape. So now that structure is a much stronger structure. Okay? All right. So I don't know if they still do this kind of stuff, but back in the old days, so when you build a structure, you build a model of it, and that's a plastic or whatever, and you can put a weight on top of the model. Okay, what this weight does is, okay, so it shows you, now when you put a weight, you want to figure out what joints are bearing the greatest stress. Now the question is, how do you find that? So if this is a plastic model, you put a weight on top of this, what will happen is if you pass polarized light through it, the greatest points of greatest stress rotate the polarized light the most. And so that's what this picture is. Okay? And once you find that, once you find which point have the greatest stress, what do? You slap extra cement there. Okay? So that's what this was about. And let me show you this demonstration. Well, I don't know if it'll work, but I was thinking about it.